All right, let's get started. So we're going to start by graphing two straight lines in the same coordinate system. One of them will have equation y equals 1/2 x minus 3, and the other one 2x plus y equals 17. Okay, so they are in, sorry, they're in kind of a different form. And in general, and this is typical to higher level mathematics, it's not like one of them is good and the other one is bad. It's more like what are you going to do with it? This form is really good for graphing. This form is really good for algebra. And we can move back and forth between the two forms, but that's not what I want to do today. So I want you to tell me, please, pretty please, points on this line. I'll give you a hint. Come up with your number for x and make it even. So when you multiply it by a half, no fractions. And then find y. So give me points on this line. Y equals 1/2 x minus 3. Give me points on it. Chop, chop. Say x is 6. If x is 6, could you put it into this expression and figure out what y is given this equation? X is 6. What is y if you can compute it as 1/2 times x? Exactly. 1/2 times 6 is 3. 3 minus 3 is 0. So we found a point 6, 0. You can come up with any x and given the equation, find the y, or any y, given the equation, find the x. But in this case, the easiest is if you start with an even number for x, because the whole thing is rigged for you to compute y in terms of x. And because there is a multiplication by half, you should start with an even number. Say x is minus 6, negative 6. What is y then? X is negative 6. What is y? Y is also negative 6. Yes, because take half of it, that's negative 3. Minus 3 is negative 6. That wasn't my intention. Kind of cute. All right, you know, the easiest one is 0. I would say let's go for x equals 0. Negative 6, negative 6. X is 0. What is y? Negative 3. 1/2 times 0 is 0. Subtract 3, negative 3. Okay, what about 10? X is 10. All right, we have 2 people to compliment me. Thank you. X is 10. 1/2 of 10 is 5. Minus 3 is 2. So we found 10, 2. In case of a straight line, it doesn't matter which points, but for precision, try to get, let's do negative 10. Will we even fit it? Negative 10. Negative 10. What's half of it? Subtract 3 and then tell us. Exactly. Okay. That's one line. All right, now we're going to graph the other one. And in this case, again, I would come up with x and then find y. Here is y. If I come up, say y is 2, then 2x plus 2 is 17, 2x is 15, x is 15 over 2. You can avoid that thing if you just start with x. Let's start with x equals, I don't know, 3. X is 3. What is y? So 2x plus y equals 17. X is 3. Y is 311. Yeah, that's not such a useful point because it's not very precise, but it's there. Okay, well, Let's try 0 then for x. No, that's even worse. Okay, how about 5 then? X is 5. Sorry. X is 5. You already have the answer. Excellent. Yes, 2 times 5 is 10. 10 plus what is 17? How about 7? So 5, 7. Now, if you see these 2 points, then clearly there is no point in, you see, it's going to go like this. So there is no point in saying x is -5 because y has to be so big that in practical terms it's useless. Instead, I would work around here. What about x is 6? X is 6. What is y? 0. X is 6. 2 times 6 is 12. We need 5 to add it to that. So 6, 5. Okay, what about 7? X is 7. Sorry. X is 7. 7 times 2 is 14 plus 3 is 17. So 7, 3. All right, x is 8. There. So the whole thing is basically, if you're lucky and you have 2 nice lines, then the 2 intersect each other at a nice point. 8, 1. Now, we're making a very important connection that will never go away. And the connection is between numbers and pictures. And it's not an either or. It's more like, can you switch back and forth? You get in trouble with one, you run to the other one. And this thing is just going to get louder and stronger as we progress in mathematics. So it's not going to go away. So now let's run to geometry. In a plane, 2 lines can behave with respect to how many intersection points. Can have intersection points. Well, they could theoretically be parallel and then none, right? Most of the time, what we're going to see is what we have now is 1. And here is the thing. 2 points uniquely determine a straight line. So if you have 2 lines that agree in 2 points, those 2 points uniquely determine both. Really, you were just given the same line twice. So all of them. You can't have just 3 points in common. It's an all 1 or nothing. Yeah, all 1 or nothing. All points. And we have these 2 lines. Y equals 1/2 x minus 3. Now we think 8.1 is an intersection point. Think of the intersection point as a point that sits on both lines. So 8,1 should work with this equation. X for 8, 8 for x, 1 for y should make this equal sign true. Does it work? 1/2 times 8 is 4, minus 1 is, minus 3 is 1. So 1, does it equal 1/2 times 8 minus 3? Yes. And the other equation, 2x plus y equals 17, should also work with x equals 8, y equals 1. 2 times 8 is 16, plus 1 is 17. So we can make one item out of this. Either you see this or a sort of embracing it as one big item. or sometimes you will see the equations labeled as first equation, second equation. And this is now algebraically is what's called a system of linear equations. And a solution of a system is a pair of numbers that works with both equations. It's a simultaneous solution of both equations. That's the solution of the system. Solution of a system. So here we are, we started to solve linear equations, and then we solved linear inequalities. And now this is again an application of solving linear equations, even though there are two variables, but once you come up with X, you solve for the Y using linear equations, so solving linear equations. So it's this close. And there are going to be 3 techniques, but mainly just 2. Of solving, how do we solve a system of linear equations? And by the way, most things can be solved with either an equation or a system. So these are big ones, probably more system actually. So a very, very useful, most frequently used construct. Okay, so how do we solve them? So graphically, that only works if the intersection point is nice. What if the 2 lines intersect each other? Like so, right? That's not going to give us much. So I don't believe that really graphically solving a system is really kosher. There are going to be 2 algebraic techniques. One of them is called substitution. And the other one is called elimination or addition. It's a really strange thing, because right now, this is algebra 1. So I'm supposed to show you this. This is algebra 2. So I'm not supposed to show you this, but I want to show you both. And I'm going to start with elimination because I think it's sweet. I like it so much more than substitution. Now, let me tell you a little bit about these 2 techniques. In this class, there is a perfect overlap. So if you decide that I only want to learn substitution, I'm not going to use the other one, you're going to be fine in this class, 100%. Or you go the other way around, you don't want to learn substitution, you want to learn elimination. In this class, you're going to be 100% covered. So there is a complete overlap. But then these 2 techniques will be necessary once the system of linear equations get worse. And there are 2 different ways of how to get worse. If it goes up in, for example, imagine that you have not XY, but XYZW. Generally, the rule is, oh, you have 4 variables, you better have 4 equations. And then you can solve it, but oh my God, substitution would hurt like hell. Elimination is the way to go. When you have many equations, many variables, and when you start organizing those things, that's how we got into matrices. Soon I'll show you a matrix, maybe today. But another way of systems to get worse is we don't go up in the unknowns, just the degree. What about the quadratic system or a degree 3 system? Then substitution is the way to go. But none of them is in this class, not even in the next one. It's 2 classes from now on. So right now, it's perfect coverage. You can ignore half this class's material. All right, so let me use, I'm going to come up with another system, and I'm going to show you elimination first because it's my favorite. And then I'll show you substitution as well. None of them I really like. Okay. So here it is, 3x plus 2y equals to 10 is the first equation. And the second equation is minus 2x plus y equals to negative 9. Okay. So first of all, it is going to be important that you understand what you're doing, and you have to know which is the first equation, which is the second equation. So my recommendation, carry the whole thing as one big beast. Don't let it fall apart. Like people who let an equation fall apart, you should have a left-hand side, an equal sign, and a right-hand side. People who let that go usually end up messing up. Same thing, don't let this fall apart too much. You should always know which is the first equation, which is the second equation. Here are the only two things. So I'm going to show you elimination or addition method. So here are the things we can do. We can multiply both sides of an equation by a number. It has to be the same number on both sides, right? A number. And we can add and subtract equations. Just think about it this way. If A equals to B, then really A and B are identical. It's the same thing. And C equals to D, same story. And then, of course, A plus C equals to B plus D. Or A times C equals B times D. Because A is the same as B and C is the same as D, really. But of course, we don't know, it's not that obvious here. But basically, you are always allowed to add or subtract equations. You can also multiply, but that's not going to help. Okay, I would say never subtract. I never subtract because equations have more than one negative sign. To subtract is to add the opposite. So I will always, until this day, even when I'm not teaching, multiply by -1 and add. I never subtract. Try not to do that. It's just too dangerous. Multiply by -1 and add. Multiply, yeah, add the opposite, right? By -1 and add. And when I was teaching you, we did order of operations and why -2 squared with and without the parentheses are different. And I said, it's a very useful thing to know that a minus sign in front of it is multiplication by -1. And to subtract is to add the opposite. I was thinking about equations and long expressions. If you try to mentally subtract them, you're going to mess up. Eventually, by the time you're at the end, you forget that you're subtracting it. So try to avoid that. The longer something is, the more plus minus signs are there, the more dangerous it is to mentally subtract. I would say don't do it. Will you mark wrong if you do it? No. But you're going to mess up. Then you will be marked wrong. And I will add, I told you so. So consider yourself more. So here's what I'm going to do. Here is the plan. Leave alone equation 1. Multiply equation 2 by -2. And add. Okay. So don't worry about y because you will see y. The first equation is 3x plus 2y equals to 10. And now both sides, we're going to multiply this by -2. Negative 2 times minus 2x is plus 4x. Negative 2 times minus 1 is minus y, plus y is minus 2y. And negative 2 times negative 9 is 18. Why did I do that? Because now when I add, y is eliminated. That's why I like the word elimination. And it's always in the addition. So both words are correct in a way. So now the coefficients of y are opposites of each other. So when we add these two lines, we get 7x, no y. And then the equation that we left with is pretty simple, isn't it? X equals 4. Now, when you found one of the two unknowns, the problem is over. It's no longer a system. You take x equals 4 and you take it into any of the two equations and you solve for the missing value for y. Should be the same, obviously, right? If we take the first equation, 3 times 4 is 12. So we take this information into the first equation, 3 times 4 plus 2y equals 10. 12 plus 2y is 10. 2y is negative 2, y is negative 1. And then put it together for your teacher for their mental health. We found 4 negative 1. Okay. So yet I want to do another elimination. Suppose we just got to here that we found x. And instead of just taking this value and exploiting it, I want to do another elimination where I'm going to eliminate x and solve for y. Because this is always possible. Just look at the coefficients, 3 and negative 2. The best way we can handle that is they can meet at 6 and negative 6, right? So that means that the first you have to decide whom to go after. So when I said, oh, I'm going to go after y, then I wanted the two coefficients to be opposites. If you leave this alone and you multiply it by negative 2, you're dead. This is a little bit tougher. These two cannot meet, it has to be divisible by 6, basically. So we could multiply, but the signs are already aligned, and I like that. I actually prefer that, because negative signs are dangerous. So we need to double the first line, triple the second line, and add to eliminate x. And I think this sort of illustrates that there is always, at worst case scenario, just multiply the two, but they can always be made opposite coefficients. So to find y, eliminating x, just for practice and demonstration, so we're going to take the first equation, we're going to multiply it by 2. The second equation, we're going to multiply it by 3 and then add. That's the plan. So the first equation doubled is 6x plus 4y equals to 20. Don't forget the other side. It's a common mistake not to multiply the other side. And we're going to triple the second equation. We get negative 6x minus 3y equals to, we're tripling, negative 27. And now when we add the two equations, boom, boom, x is now dead, y is almost falls into our lap. By almost, I mean, we didn't get that 1y equals to, we got 7y, but it's pretty sweet. 7y is negative 7, therefore y is negative 1. So that's how you do elimination. Are there any questions? All right, let's do another one. Actually, let's do the one that we already solved graphically. What did I say at the beginning? That this form is good for graphing, this form is good for algebra. So basically, we're going to manipulate this until it looks similar to this. So we have y equals half x minus 3 and 2x plus y equals to 17. In fact, ax plus by equals to c, a form like a bunch of x plus a bunch of y equals to a number. It's called the general form. And it's good for computing. Now, to bring this to the similar form, we're going to start with, I want to clear the denominators. We're going to multiply everything by 2. So then 2y, 1x, 6. Do you understand why? The slow motion thing would be 1 half x minus 3 was multiplied by 2, and then we distribute the 2. 2 times half is 1. That's why we selected 2. And 2 times 3 is 6. And then we're just going to work on bringing them on the same side. Now, you might wonder, should I subtract x? Should I subtract y? If you subtract x, you're going to have them together on one side, one positive, one negative. Same thing with the y. I guess at, I don't know. Well, I'm picking in front. I would work against the negative sign. So I would say, okay, let's do it so at least that 6 is positive. So if I add 6, 2y plus 6 equals x, and then we subtract the 2y, 6 is x minus 2y. Of course, we're going to rewrite it as x minus 2y equals 6. So x minus 2y equals to 6 was one equation, the first one. And the second equation was 2x plus y equals 7. Okay, so very similar. So now we sort of make a strategic decision as to should we go after eliminating x or eliminating y. And it's almost the same because the numbers are literally the same, 1 and 2, 1 and 2. So that means you can leave alone one, double the other. But this one, the signs are set up. So I would eliminate y because then we don't have to worry about multiplying by negative numbers. So to eliminate y, leave alone the first equation. And the second equation multiply by 2 and then add, which is always the last step. So the first equation is x minus 2y equals 6. The second equation we double, 4x plus 2y equals to 34. Right? That was the goal. And now when we add, y cancels. Now, you can cross it out like that, but make sure I can really don't, darken it out. It should be readable weeks later. Actually, you do not have to cross it out. I don't think it needs explanation. 5x is 40, x is 8. Now remember, we solved this geometrically, graphically. We graphed it and the intersection point was 8, 1. And just for kicks and giggles, so we no longer need to do elimination. We can take x equals 8, 8 minus 2y is 6, 8 minus what is 6? 2. So 2y is 2, I is 1. Easy breezy. But just for practicing, let's eliminate x. So to eliminate x, what should we do to eliminate x? Well, we have two options. To eliminate x, we practically leave this alone and we double it, and then one of the two needs to get a minus sign. One of the two has to be multiplied by -1. So either this gets a -1, this gets a -2, and this is left alone, or this gets the 2, this gets the minus. And again, I would say, this is all three are plus, I don't want to mess with that. This one at least has one minus. So what I would do is I would multiply the first equation by -2, so -2x plus 2x, and leave alone the other one, and then add. So the first equation, we're going to multiply it by -2. So that's -2x plus 4y equals -12, minus plus minus, and then leave alone the second one, 2x plus y equals to 17. It's kind of cute that we always, not always, but very often we divide by that same number. Here we had 5x, now we're going to have 5y equals 5y equals. Any questions? You sure? All righty then. So I by far prefer this method to the one. This I'm not even supposed to show you yet. It has to be kept secret. No, it's strange that in our curriculum it would be algebra 1 for one, algebra 2 for the other. It's weird. Usually it should both be covered in algebra 1. So substitution. Now the word substitution is already floating around, right? Substitute, when we evaluate an expression, we're substituting the number into the letter. The specific technique of solving a system of equations using substitution is something specific. It refers to something more specific than just, I'll show you what. So we're going to solve the same problems using substitution. Was the first one. First one we solved was vx plus 2y equals to 10, and minus 2x plus y equals to -9. Okay, so as in elimination, we started with a strategic decision as to should we go after x or y, but none of them is much harder than the other, sometimes. But here we're going to have to make a decision that's very important to get right. Not to get it incorrect or versus incorrect, but strategically. The first thing we have to do is we have 4 choices. Pick an equation, and in that equation, pick an unknown. So select an equation and an unknown in it. We have 4 options, right? X from the first, Y from the first, X from the second, Y from the second. And the second step will explain why there is just one decision here that is far better than all the other 3. Step 2, solve for that unknown in terms of the other unknown. Now, when you have 2 unknowns in an equation, most of the time you cannot solve for one unknown like it's 5, but you can solve it in terms of the other unknown. Step 3. Well, I'm going to start demonstrating the steps, illustrating them. So the best choice is, and I'm going to show you what happens with the worst choice too, because sometimes you're not going to have a good choice. So you should see how to get out of a pesky situation. So the best choice is y in the second equation. Simply because when we solve for y, the last step will involve we don't have to divide. When we solve for x here, which is the worst decision, the last step is gonna be a division by 3. So the best choice, y in 2, because in the second equation, y equals 2x minus 9. You see what I did? I just put the 2x, I added 2x to both sides. The worst choice would be x in the first equation, because 3x plus 2y equals 10. Now we're going to subtract 2y. 3x equals minus 2y plus 10. I like to put the number first, the letter first. So not 10 minus 2y, but negative 2y plus 10. And now we divide by 3, negative 2y plus 10 over 3, or negative 2 over 3y plus 10 over 3. Is there anyone who needs to see why we can make this step? Basically, to divide is to multiply by the reciprocal. So you have to multiply minus 2y plus 10 by 1/3 and now the distributive law. So we distribute divisions as well. Instead of divide by 3, multiply by 1/3, and then they both get it. But you see, this is a much harder expression than 2x minus 9. Basically, you had a chance to avoid fractions and you didn't. You chose not to avoid dealing with fractions. And 3 is worse than 2, because when you divide by 2, you can still have decimals. But division by 3, you have those terrible repeating decimals. Like 5 over 2 is okay. It's a fraction, but it's a fraction that doesn't look bad as a decimal. Try 5 over 3. Not so good, right? So that's why between these 4, this 3x was the worst choice. Okay, so step 1 and step 2. Step 1 was select y in second equation. Step 2, solve for that unknown in terms of the other one. So we grab the equation we selected and we isolate our unknown. Now comes the step that is the reason why it's called substitution. And this is really important that you keep step 3. We substitute 2x minus 9 instead of y in the other equation. It has to be the other equation. In the other equation. So we got y, we expressed y in the second equation. We have to grab the first equation. And the first equation, which you're not going to have to repeat, but this is it. But now, the step that we call substitution, that we're going to write 2x minus 9 everywhere we see y. So this equation is going to be adjusted by, we substitute 2x minus 9 into y. This was just 2y, so 2 times 2x minus 9 equals to 10. Now, if you look at this equation, in a way, we achieved the same thing as we achieved with elimination. Now we have an equation in just one unknown, so we can solve for it. And then once we solve for it, always circle what you substituted. This is the place to go. Once you know what x is, hey, y is going to be twice that minus 9. And this is a friendly little linear equation. So we have 3x plus 4x minus 18 equals to 10. 7x is 28. Oh la la, x is 4. We already solved this, so we should get the same numbers, right? Now that x is 4, I always circle the thing to be substituted, because that's where you should go back for y. So that means that y, which is always twice x minus 9, is now 2 times 4 minus 9. That's 8 minus 9. That's negative 1. Did we get negative 1? I forgot what we got. We should get the same answer. Yeah, 4 negative 1. So we're good. Okay. Any questions? Now let me show you. Now, suppose you have an equation where you don't have a good choice. Suppose everybody, all x, all y comes with a number multiplying it. 3, 2, -7, 13, terrible, terrible numbers. Then you don't have a good choice. So I want to show you what happens when you either didn't have a good choice or you foolishly made a choice that makes your life hard. So basically, I'm just going to finish this problem to the bitter end. When we chose, I'll start from scratch. So the first equation was 3x plus 2y equals 10. And the second, I forgot to do something. And the second equation was minus 2x plus y equals to -9. And our worst choice was, so for x in the first equation, and then we subtract 2y and divide by 3. So if you recall, x was minus 2y plus 10 divided by 3, or negative 2/3 y plus 10 over 3. I'm writing down both forms because very often one of them is much better than the other, but we don't know which one yet. And actually, it depends on your technique. With my technique, this is good enough. Make sure you understand that the minus is just for, not for the whole fraction, just for the 2y. Okay, and now for the substitution step. This information, we sort of sucked out the information from the equation, the first one, and we're going to inject that information into this other one, which is the second one. It says minus 2x plus y equals -9. Minus 2x, but x is now this, minus 2y plus 10 divided by 3. Second equation plus y equals -9. Now, I don't know about you. You can treat this as a linear equation with fractional. You can use this, and then I should probably show you that. But first, let me show you the one that I like. Is just wipe out the denominator. Just multiply everything by 3. If you multiply everything by 3, what we get is -2 times minus 2y plus 10 plus 3y equals to -27. See, it didn't hurt so much. And now we're back to regular, normal. So it's not such a terrible thing. Minus 4y minus 20, no, plus 4y. 4y minus 20 plus 3y equals to -27. So 7y is, we add 20. 7y is -7, so y is negative. And then what was the substitution? X is minus 2y plus 10 over 3. So now that we know that y is -1, is -2 times -1 plus 10 over 3. That's 12 over 3, that's 4. So we got the same 4, -1. Okay. So this is by far my favorite technique. But I want to show you another one in case, you cannot debate tastes. So let me show you another way of dealing with this. It's basically just saying, oh, fractions, same thing. So we can say -2 times. So this is the step where we substitute the information from the first equation into the second one. -2 times x, but instead of x, and I'm going to use this one, minus 2 over 3y plus 10 over 3 plus y equals to -9. At any point, you can multiply by 3. But now I'm just going to say, hey, I don't mind, they are fractions. -2 times -2 over 3 is plus 4 over 3. That's how many y we have. Minus 20 over 3 is -2 times 10 over 3 plus y. But I'm already thinking about 3y over 3, right? You're going to combine these two. equals to -9. Add 20/3 to both sides. And then these two, see, I already got ready. So this is 7/3 y equals to -9 plus 20/3. I'm going to write -9 as -27/3 plus 20/3. 7/3y is -7/3. We divide everything by whatever is multiplying y, and that's how we're going to get y equals -1. So basically say, I don't mind that they are fractions. Same thing. You decide which one you prefer. I like to just clean out the denominators in the first moment possible. Notice that none of them happens when you do elimination. We don't have these fraction thingies. Okay, any questions? You're still here, right? Just enter into the, yes, thank you, yeah. Thank you, that's it. Thank you. In my morning class, I did this, and out of 7, only 2 people ticked. 2 people, you know, gave me a sign of that they are there. So the other 5 were somehow didn't know that I was asking that. I think they were gone. So hey, this is not much better. Pumpkins, could you please, if you're still in front of the computer, could you just put it in the chat box privately for me that you're still here? I want to know you're still here. Cool. Good. One more. That's it. One more. That's it. There's 4 people ignoring me right now. 1, 2. There you go. There you go. Okay. Most of you are here. Thank you. I know. I'm ready to start the spring break too. You know, next week we don't have classes. All right, everybody's here. Good. So what I'm going to do is I'm going to solve that last problem with substitution. I think that last problem was also our first problem. No. There was this x minus 2y equals 6 and 2x plus y equals 17. We have 2 good choices. X from the first one or y from the second one. One of them is slightly better. What would you want to do? Solve for x in the first one or solve for y in the second one? And why is that slightly better than the other option? X from the first one or y from the second one? And why? All right, so if I solve for y here, what I would get is y equals negative 2x plus 17. Here, plus 2y plus 6. So I would go, because I don't like negative signs, plus 6 is smaller than, I think maybe, so I would go in from the first equation, x is 2y plus 6. And then shove that in the second equation, which is going to be 2 times x, but not x. Always circle that because this is where we circle that. 2 times x, but x is really 2y plus 6 plus y. 2x plus y equals 17. So 4y plus 12 plus y equals 17. 5y is 5, y is 1. And then, and that's maybe one advantage of substitution. After the first unknown, the second one is very quick. X is 2 times 1 plus 6. That's 8. So we found 8, 1. Even though we found y first, it's still the y. That was our first example. Damn it. I'm sorry. I don't like what just happened, but the first example came in a different form. So one more time, the same problem. Sorry. Well, I'll pick up. Also, let me show you what happens if you accidentally take the information back into the wrong equation. If you sort of suck out the information from an equation, and then you take it and you re-inject it, you're going to get something silly like x is x or 0 is 0. So don't. But I want you to see what happens. So you have to keep track. This information is from the first equation. You have to take it into the second. Now I'm going to accidentally take it into the first one. So x is 2y plus 6. That's x minus 2y equals to 6. You see, you get that 6 equals 6. Like, so it basically really doesn't work at all. In fact, the numbers will tell you that you took it to the wrong equation. All right, so what I don't like about this is that this thing maybe was born for substitution, because look, even though this has fractions, it is already solved for y. But I caught it in the wrong form. I didn't look at page 1, I looked at page 2. So I'm just going to make up something similar to this. Oops, this is a smart book. All right, so 3x minus y equals 10. And x equals 1/3 y minus 2. See, it's kind of similar to, now you can always work on this. Multiply by 3 and then bring x and y into the same side. That is always an option. And I would probably do that because I prefer elimination much to substitution. But if substitution is the way to go, this is already ready. X is expressed. So we're just going to say, okay, well, from the second equation, we have this. Let's take it into the first equation. It says 3x minus y, but we have an expression for x. So the equation is 3x minus y equals 10, and x is now this 1/3 y minus 2. And you know, we will not need to clean the denominator because this 3 takes care of it. Right? 3 times 1/3 is 1. So we get y minus 6. Did I take it to the wrong equation? Oh, no. I'm sorry. Okay, I found a typo. All right. We're just going to do that one then. This is a typo. Sorry. So what was it? We're just going to do the original then. Sorry. So y equals 1/2 x minus 3 and 2x plus y equals 17. Speech is the same. If substitution is the way to go, well, we already have this expression. We can just substitute this into the second equation. So everywhere where we see y, we're going to write 1/2 x minus 3. So we have 2x plus y. Y is 1/2 x minus 3 equals to 17. This is 4/2x plus 1/2x equals 20. 5/2x equals to 20. 5x equals 40. It's up to you when you multiply by 2. This was so benign that x is 8. And then y is 1/2 times 8 minus 3. Which is 4 minus 3, which is 1. All right. Any questions? Oh, I just saw your answer. You want to do x, and you're right. Oh yeah, that was a long time ago. So, okay. Now, gonna be lots of word problems. And there is a huge overlap between, you can treat it with an equation and one variable. Huge overlap. For example, you remember those word problems, and one side of a rectangle is 5 less than 3 times the other side. Perimeter is given. Well, you can say x and y, and then one of the equation will say that y equals 3x minus 5. And the other is the perimeter, 2x plus 2y equals to, I don't know, whatever is given. So they're this close. A lot of the problems, you can handle it with just an equation just as easily as with a system. But there are some problems that naturally lend themselves to equations or naturally lend themselves to systems. I'm going to show you problems that I think naturally lend themselves to systems, in the sense that you're not going to have a comparison sentence like, oh, one side can be expressed in terms of the other side. That kind of lends itself to equation. I'm going to show you a very cute little problem. That was the first application of systems that I've ever seen. And I think it's a really cute problem. So we are on a farm where there are chickens and cows live. All healthy, no funny business. Chickens, cows. And the farmer must be in a funny mood, because when he's asked how many chickens and how many cows he has, he's not telling us, but he says that there are 100 heads and 320 legs. How many chickens, how many cows? So what makes it more systemy than before, that you don't have a sentence that the number of cows is 4 less than 5 times the number of chickens. You don't have an easy comparison. And then we're just going to go with a system. And if you forgive me, I'm going to do elimination when we solve the system. Let's say we have X many chickens and Y many cows. And you should write this down. Don't make me have to go and decode your computation, because you're not telling me what is what. Now, we're going to have two equations, because if you establish two variables, we need two equations to solve for them. That's often a debate, you know, with the big geometry problem. It's like, okay, A, B, X, now I need 3 equations. Maybe I don't need all 3 of them. And that's a debate. So the first equation will express that the chicken heads plus the cow heads is the total number of heads. Can you state that equation with X and Y? That equation translated. Oh, here is the data. Basically, we have 100 heads and 320 legs. So what would that equation be? Just state the number of heads like this. Exactly. X plus Y equals to 100. Now you could say, well, I know we don't need a system here, because if one of them is X, the other one is 100 minus X, which you can get very easily if you solve for Y here, right? So it's tomato, tomato. The second equation will express the number of legs. So the chicken legs plus the cow legs is the total number of legs. How does that equation go with X and Y? No, that would be a sad gathering, because how many legs per chicken? How many legs per cow? How many chicken legs? Exactly. Exactly. The number of chicken legs is 2x in terms of X. The number of cow legs, it's a really cute problem. And that's how we get the number of legs. Now, The minute you whipped out as many equations, as many unknowns, the word problem is over. Now you have a pure algebra problem, a system. But I want to, it's the opposite of warn you. I'm going to encourage you to slow down and look for simplifications, because healthy animals means this can be divided by 2. A lot of the coin problems, you know, we'll do that next. We have 200 coins, all nickels and dimes. Well, nickels and dimes, you're going to be able to divide by 5. And that's kind of typical. So take a second or two to look for simplifications. Instead of scaling this up, maybe we can scale this down, and not, but almost. So we have 2 equations, x plus y equals 100, and 2x plus 4y equals 320. And I think, let's just go and kill x. So that means this is going to get a -2 multiplier. This we're going to leave alone. So then minus 2x minus 2y equals minus 200. And 2x plus 4y equals 320. Add. X is dead, 2y. Y almost falls into our lap. Is 120. So y is 60. And then if the first equation is as simple as that, then we know that x is 40. And then don't stop there. No one asked you about x and y. This was a word problem. So write down what we think the answer is. 40 chickens. X was chickens. X was chickens, yes. 40 chickens, 60 cows. Okay, so the legs is, no, the heads. The head count is right. And the legs, well, you multiply this, so the legs, the chickens contribute 80, the cows 240, and when you add those 2 up, you get 320. So it works. So forget the system, because you may have correctly solved the wrong system. Just take your solution, interpret it to the bitter end, and then check against the conditions stated in the problem. Basically, when a problem lends itself to systems of equation, my professor would call it a classic chicken cow problem. For example, let's talk about those jar of coins. So let's say we have 200 coins, all of them nickels and dimes. And if you don't know this during exam, you can ask me how many cents is a nickel, how many cents is a dime. That's not something we kind of assume that you know, but we don't have the right to assume that. All nickels and dimes, 5 cents, 10 cents. How many of each? If the total value is of all coins is $6.80. And my professor would say, okay, so this is a classic chicken cow problem where nickels are chickens with 5 legs and dimes are cows with 10 legs. And so there's going to be one very basic equation for the number of coins, and the second one for the value of the coins. So 2 parallel information, not one is compared to the other. So let's say we have, okay, so suggestions. Use either X and Y or N and D, or if you like N and D. What I want to advise against is complicating things like N would be the number of nickels and number of dimes. That's pompous and hard to read, hard to write. I would say don't do it. But you develop your own style. I usually go with X and Y because I'm so used to reading them during computation. My Z can be read as a 2. My T can be read as a plus sign. So X and Y are kind of safe. But if you want to go with the letters, that's fine too. So, but then we have to say, let X be the number of nickels and y, the number of dimes. So the total number of coins. That's an easy equation. Give me an equation expressing the total number of coins in terms of x and y. No, the number of them, not the volume, the number. It's the heads, the equation for the heads, not the legs. Yeah, oh no, x plus y equals 200. You're overthinking it. Yeah, we have x is the number of nickels, y is the number of dimes, they add up to 200. Usually one of the equations are pretty simple. Now, the second one, you actually made an important mistake, and I kind of set you up. I primed you. I kind of made up, this is the power of suggestion. So this line that I'm going to write is wrong. And you're going to tell me what's wrong with it. Here is the problem. You have to make up your mind. Are we going to express things in dollars or in pennies? Because the two sides have to be consistent. The right-hand side is in dollars. This side is in pennies. So you have two options. Either think in pennies. So express both sides as pennies, then it's 5x and 10y, but then that's $6.80 is 680 pennies. And notice that the first thing you should do is divide by 5. Or think in dollars, which I'm going to talk you out of it, because in dollars, you can see 5 over 20 or 0.05, not 5 over 20, 1 over 20, 5 over 100 or 0.05 x plus 0.1 y equals 680. The first thing I would do is multiply the whole thing by 100 to clear these decimals. This needs 10, but this needs 100. And if you multiply it by 100, that's nothing else than switching to pennies. We're going to get 5x plus 10y equals 680. So might as well just start thinking in pennies. There's no point going into dollars here, not unless you prefer these yucky decimals. So that's just my suggestion. Just think in pennies in these point problems. So we have the two equations. The first equation is x plus y equals 200. And for the second one, I would want to divide by 5. You see they're all divisible by 5? And unless pennies are in the mix, quarters, dimes, nickels, these are all divisible by 5. 680 divide by 5. 136 x plus 2y equals okay. And then maybe now you get away with subtracting. Why? Because there is no, something is wrong though. We get a negative answer. What did I do? $16.80. It has to be 1680. I'm terrible. Sorry. So 1680 divided by 5 is 336. So I told you never to subtract. Maybe this is an exception. There is no minus sign. What happens if we subtract the first equation from the second one? Y literally falls into our lap, right? Just subtract the first equation from the second one. But if there is just one minus sign, I would say don't. X minus X, gone. 2y minus y is 1y, and then 136 is 336 minus 200. And then if y is 136 and x plus y is 200, then x is 4 plus 6, 64. So we match that with the, okay, so we think that there are 64 nickels and 136 dimes. So let's check 64 plus 136, that is 200. And then, well, the dimes, that's easy. That's $13.60, right? Each dime is 1/10 of a dollar. And 64 nickels is 3.2. And that's 16.80. So we're good. Now I cannot, any questions? So the problem with my first number was that not in all cases, but in this particular case, because there are nickels and dimes, I can name any number divisible by 5 as long as it's between two particular numbers. What if all 200 are nickels? If all 200 are nickels, it's still already $10. There is no way it's $6, right? That was the problem. And if all of them are dimes, that's $20. So any amount between $10 and $20 is doable, as long as it's divisible by 5 at the very end. So that was way too small. And you should never do trial and error. A correct trial and error problem is worth so much less than a messed up algebra, messed up, smelling like sweat, bad algebra. Because when you do algebra, you're trying. When you do trial and error, you say, I don't even want to try. I'm not learning algebra. I'm just going to find my way around it. Okay, any questions? I saw a really, really cute problem that boiled down to a system of equations. So we have a room that is 140 feet squared or square feet. That's the area of the room. And we have 3 rugs. With the total area, we don't know how big each of them is. Turns out we won't have to know. But with a total area of 200 square feet. So we cover this room with the rugs, but obviously the only way this is possible, nobody's rolled up. So what's going to happen is that certain parts of the floor are covered with more than one rugs. Like they're not side by side, but one rug is on the other one. The area that is covered by exactly 2 rugs is 24 square feet. What is the area that's covered with 3 rugs? Any ideas? You know, you can, I'm pretty sure that you can do sort of a quantitative reasoning, like we counted this, let's subtract the 24, but I'm actually not that smart, but I'm an algebraist, so I immediately went for systems. And what I said, it looks like there are 3 unknowns, but actually one of them is given. So we could say, it wasn't my first idea, but I bumped into it pretty quickly, that let X denote the area covered with one rock. And then Y denote, but not for long, the area covered with 2 rocks. And then Z would be the area covered with 3 rocks. But that's not going to be necessary because Y is given to be 24 feet square, right? So it's really going to be, X is going to express the area covered with 1 rock. 24 is the area covered with 2 rocks, and then Y is going to be the area. Actually, I went with A, B, and C. That's another very natural system notation. All right, so the whole room was covered, and that means that if we add these 3 together, we should get the room size, right? So X is the area of the room that is covered with 1 rock, plus 24 is the area of the room that is covered with 2 rocks, plus Y, that's the area that's covered with 3 rocks, has to add up to the whole room because we covered the whole room. Okay, now what? What data have we not yet used? What number have we not yet used? The 140 is here. There are 3 numbers in this problem, 140, 200, and 24. 24 is here. Actually, 24 and 140 are there. So the only thing we haven't used is 200 feet, square feet. And that's where the problem becomes cute. Now, let's say we want to express the area of the total area of the rocks. It's sort of, now we're counting not floor area, but rug area. And I think it goes like this. If we remove the rocks and we just lay them next to each other, we would get 200 square feet, right? But some of them are on the top of each other. So, well, we can count is that, so I called it rug area, X. That's an area that's covered with 1 rock. And then 24 times 2, this is the area that's covered by 2 rugs, is 24 square feet. So the rug area is twice 24 there. And Y times 3 is the rug area of the part that's covered by 3 rugs. I'm not sure if I'm explaining it nicely, but this should add up to 300, right? Certain parts are overlapping. If you just add the area, is 140, but if you add the rug area, then the double ones you count double, the triple ones you count triple, and then you're actually, so we have X plus 48 plus 3Y equals 200. It's just a lovely I just really think it's cute. Now we clean up. But you see, again, that's a nice thing about system of equations, that usually they boil down to easy algebra. Like the nastiest systems will not come out of word problems. They're just going to be given here, solve it. All right, so we can subtract that. So the first equation is x plus y equals 140, 120, 116. And the second one is x plus 3y equals to 152. All right, now solve this system. You can almost do it visually in your head. Again, no minus sign, so maybe this is safe enough to subtract. Either way, go get it. Tell me what x is, tell me what y is. What is x? What is y? Chop, chop. Come on, solve this system. Easy breezy. So the chat box says, I don't understand how you decided what number to work with from the beginning. You mean from the 140, 224? That's still no reason for you not to solve this. I can still answer how I got to those numbers. No, I know we need to start with x plus y equals 116, but how do you decide what x equals? No, this is, so these two equations are just these two equations cleaned up. The first equation counts the area of the floor. This counts the area of the rock. Imagine that, I don't know, I'm going to draw a weird picture. So suppose this part is covered with one rock, and this is what we call x. And this part is covered with two rocks. Really weird picture, but, and that's 24. We know this is 24. And then this part is covered with three rocks. And this is what we call y. So how much rock lays on this part of the room? X. How much rock lays on this part of the room? Well, 24 is the size, but there are two rocks on it, right? So it's 48. And then this one, how much rock does this represent? Each square feet is covered with, every spot is covered with three rocks. So the floor area of this is y, but the rock area is 3 times y. If you want to combine, if you follow the area of the rock. And that's how 1 times x plus 2 times 24 plus 3 times y equals to the rock area. This is the heads, this is the legs, so to speak. That's what was cute. I mean, I should have made you suffer, and you would have come up with it eventually. But I just thought it was a cute application. And then if we clean up, we get this. And then I was hoping you guys would solve this system. Oh, and I had another fun one. So I just want you to solve this system of equations for x and y. If you do elimination, multiply the first equation by -1, the second equation by nothing, just leave alone, and then add. X is dead. 2y equals to 52 minus 16, 32, 38, no, 36, 12 minus 6. So y is 18. And then x is 198. And so, and if you do substitution, well, y is 116 minus x from the first equation, although I would prefer swapping them, and then minus x plus 116. And then it's x plus 3 times 116 minus x is 152. There it is. X plus 348 minus 3x is 152 minus 2x equals, my hunch is twice -19. What's that? Minus 196. Not sure I understand why no one solved this yet. Yeah, so x is 98. So this is with elimination, this is with substitution, this is with elimination. And so what we got is that 98 square feet is covered. That was x. X was the stuff. I'm missing the page. X was the stuff that was covered with one layer. 24 square feet was covered with 2 layers. So, and the rest one was 18 square feet with 3 layers. That should add up to the room. Do we have 200? 8 plus 8 is 16, plus 4 is 20. Yeah, 140. Now, to account for the area of the rock, 98 square feet is covered with 98 square feet of rocks. 24 square feet is covered with 2 layers of rocks. So as a rock area, that's 48, and you have to triple this because each square feet has 3 rocks on it. And then when we add, that should add up to 200, does it? 4 plus 5. Yep, it does. So that's how that one went. I'm not sure I understand. Oh yeah, I was looking for this. Okay, I have one more that I find cute. So A and B are talking. And A says, give me $10. Then we will have the same amount of money. And B says, no, give me $10 and then I'll have twice as much as you do. I actually used A and B for this one. So each statement is going to give you a cute little equation. So let's say right now A has A and B has B. Translate that if B gives A 10, they would have the same amount. So translate the first statement into an equation in terms of A and B. If B gives A $10, they will have the same amount. It's not that it's hard, it's just cute, because what happens if A gets $10, then A will have A plus 10, but where did A get that $10 from? B. So B is gonna be, this is what it looks like when B loses $10 and A gains $10, right? That's gonna be one equation. And the second equation is gonna say that if A gives B $10, B will have twice as much. So the two people is gonna be the other way around. Instead of A gets 10 and B loses 10, A loses 10 and B gains 10. And the equation should say that this guy now has twice that. There. I find that one cute too. So it's not exactly the 2x plus 3y. You have to work on it, but it's pretty, as I said, word problems. The first equation will say, if you add 10, there is going to be 20 here. So B minus A is 20. That's the first equation. And that makes sense. If you have $70 and I have 50, you give me $10, we will both have 60. Basically, the first equation translates that you have 20 more than I do. But it wasn't obvious to me before we did the system. And then the second equation says if A loses 10, that's going to have to be multiplied by 2, so we get B plus 10. So that's 2A minus 20 equals B plus 10. So 2A equals B plus 30. We can just add in this form and B will cancel out and A falls into our lap, right? Let me, this is minus B plus 2A. So when we add, B cancels out and A is 50. And then B is 70. Does that work? All right. If B gives $10 to A, they will both have 60. But the other way around, it's going to be 40, 80. So indeed, A will have half the money of B. I find that problem cute too. I'm sure you do too. All right. Any questions? Okay. Then I'll stop here. Thank you guys.